Alright, so let us start with the definition of a vector and the three possible interpretations of a vector. Okay? Look, when I say definition of a vector, the textbook definition, well, all of us know it. What is the definition? A directed line segment. Okay, a directed line segment is a vector. Now, although we say a directed line segment, we show it like a ray, isn't it? We show it like a ray because we want to emphasize that it's along this direction. So if we say this, then it is going to give us a different vector, correct? Now the terminology. If I call this point as P and if I call this point as Q, then the vector is PQ bar, also written as PQ bar, or NCERT uses the bold notation. Okay, bold notation means it's a vector quantity. So if you see your physics textbook, all the quantities which are vectors, let's say force, electric field, magnetic field, velocity, torque, you can see all of them being written in the boldface notation. Why? Because that's a vector quantity. Okay. What is the initial point? Initial point is where the vector begins. Terminal point is where the vector ends. And what is the magnitude? Magnitude is the length of the vector. Okay. This length is the magnitude of PQ bar. Okay. Fine. Now what are the three possible interpretations? Let us start with the interpretation that we already know. Okay. Three possible interpretations are: first, it could represent some physical quantity. Okay. First interpretation is some vector quantity. Okay. Some vector quantity. Example, it could be velocity, it could be force, it could be displacement. I'll come to displacement in a moment. Maybe you already know it, right? Displacement is a localized vector. It has a fixed starting point and a fixed terminal point, unlike velocity or force. Okay, fine. And in mathematics, we treat all the vectors as free vectors. We can translate them any way we want, anywhere we want. Number two, position vector. Okay, position vector means it always starts from the origin and ends at the point. And the third one is direction indicator. The third one is direction indicator. Okay, in mathematics, the most popular use of vectors, especially in 3 dimensions, is the direction indicator. Okay, and when we say direction indicator, what I mean is I can begin this vector from any point P. As long as I do not rotate it, as long as I do not stretch it or shrink it, it is still going to represent the same vector. Do you get this? Yes? Okay. Fine, so that's vector. Three possible interpretations. First, it could represent a physical quantity. Okay. Some physical quantity. Second, position vector. Third, direction indicator. Okay. Well, let's now see the laws of addition and properties. Okay. First law is triangle law. How do we arrange the vectors? In triangle law, the vectors are arranged head to tail. Now what is tail? Tail is the starting point of the vector. Okay. So tail of B bar is made to coincide with head of A bar. Okay. And then the third side, which begins from the tail of the first and head of the second, that is A bar plus B bar. That is triangle law of vector addition. In the parallelogram law of vector addition, how do we arrange the vectors? We arrange the vectors tail to tail. Correct? We arrange the vectors tail to tail. and the common diagonal or the diagonal which originates from the common tail is the addition. Okay, so tail of b bar coinciding with tail of a bar. Okay, and the generalization of the triangle law is the polygon law. Okay, generalization of the triangle law is the polygon law. So if I want to add a bar, b bar and c bar, what I can do is I can take a bar, then I can take b bar, I can place them, I can place b bar at the head of a bar, okay, and then I can do the same thing with c bar. Okay, I can do the same thing with c bar, same thing, and then the last one, if I complete well, let's say I have 4 vectors and I'm going to get a pentagon. Most likely I'm going to get a pentagon. Okay, and how is the resultant for addition? The resultant is initial point of the first and the terminal point of the last, or tail of the first to head of the last. That's how we add the vectors using polygon law, again head to tail arrangement. Okay, head to tail arrangement. That is law of addition. Now let's go to properties. You probably know the properties, but let's just go through them in case we are required to apply the properties. We will see that in our next class, how to apply the properties. First, commutative, vector addition is commutative. A bar plus b bar is equal to b bar plus a bar. Second is it is associative. If we have 3 vectors, want to add them, we can either add first 2 and then add the third one, or we can add the last 2 and then add the first one. Okay. Third, distributivity of scalar multiplication over vector addition. So alpha times a bar plus b bar is alpha a bar plus alpha b bar, and alpha plus beta a bar is alpha a bar plus beta a bar. If we multiply any vector by 0, then we are going to get a null vector. There's a printing mistake in here. This RHS is a vector quantity, okay? So it's not a number 0, it is 0 bar. Okay, fine. And what will be this? 1 a bar is going to be a bar. If we multiply any vector by 1, the number 1, then we are just going to get the vector itself. And if we multiply a vector by -1, then we are going to get a vector, same magnitude but opposite direction. Okay. And then there are some other properties also, like if we add a bar and negative a bar, then you are going to get a null vector. Okay. Then you are going to get a null vector. Sometimes because of these properties of null vector, we call null vector as additive identity. And the negative of any vector, okay, negative of any vector as additive inverse okay, additive inverse of a bar. Okay, just remember the names. Additive identity means on adding 0 or null vector to any vector, we don't get any change, we don't get a new vector. And additive inverse means if we add negative of any vector to the same vector, we will get a null vector. Okay? Yeah. Next, collinear vectors and coplanar vectors. Now, the idea of collinear vectors differs slightly from the idea of collinear points. Okay, see, when I say collinear points, I must say that they lie on the same line, correct? For vectors to for points to be collinear, I cannot have a point one lying on this line and the other one lying on this line. Or let's say, okay, let me just give you an example. Suppose I have a vector Okay, let's name the point. Let's say I call this point as P1, this point as P2, this point as P3, this point as P4, this point as P5, and this point as P6. Now, what are collinear points here? What are the triplets of collinear points? P1, P2, P3. These are collinear points. P4, P5, P6 are collinear with themselves, but they are not collinear with any of the other 3 points. Correct? So I can say that P1, P2 and P4 are not collinear. Why? Because they do not lie on the same line. But for vectors, we relax this requirement and we say that if we have a vector P1 bar to P2 bar, okay, if we have a vector from P1 bar to P2 bar, and suppose I have a vector from P4 bar to P5 bar, then these vectors will be parallel to each other or collinear. Okay, so we say P1 P2 bar and P4 P5 bar are collinear. So for points, they must lie on the same line. But for vectors, even if they're parallel to one and the same line, we will call them collinear vectors. Do you realize this? Okay, so let me write it general. Okay, 3.3. For any 3 points to be collinear, they must lie on the same line. Point 4. For any 2 vectors to be collinear, they should be, they should be parallel to same line. What got the difference? Collinear points and collinear vectors. Okay, and when that is the case, we can always write one vector as a scalar multiple of other. Okay, so that's b bar equal to x a bar. Is that clear? For collinear vectors, one vector can always be written as a scalar multiple of the other. Okay, fine. Now the idea of collinearity, as it differs with the idea of collinear points, same thing applies to coplanarity. Okay, coplanarity also, because for vectors we let them free, we can shift them anywhere we want without rotating them. Okay, so when can we say that vectors are coplanar? Let me add it here. Well, I really need some space, sorry. Thought I would find this enough, but I don't. Okay. Fine, maybe I can add that point here now. Two collinear vectors are always scalar multiples of each other. Okay, two collinear vectors are always scalar multiples of each other. I have given you these examples. F bar and A bar are always collinear. Realize that? No? when mass is constant. Okay, when mass is constant. Okay, fine. Just because we have covered rectilinear motion, in rectilinear motion, position x bar, displacement delta x bar, velocity v bar, acceleration a bar are always collinear. Okay, I hope you understand that in rectilinear motion. Okay, next, coplanar vectors. Coplanar vectors. Now, for lines to be coplanar, they must be on the same plane. So this gives the lines only three possibilities. Which three possibilities? Parallel, intersecting, and coincident. Okay, so for coplanar lines, only these three possibilities exist. The possibility of skew lines, we will explore it in three-dimensional coordinate geometry. Point 7. For three vectors to be coplanar, two vectors are always coplanar. Okay, for three vectors to be coplanar, they should be parallel to same plane. Okay, let me give you an example to make my point clear. Okay, suppose there is a building. Suppose there is a building which has, let us say, 3 floors. Okay. Now there is a person on the ground floor. Let us call it G. Call him G. Okay. Now velocity of the first person who is walking in his house, velocity of some other person, let us call him F, VF bar. He is walking in his house on the first floor, and let us call him S. So velocity of the velocity of the person S who is walking in his house on the second floor, all of them are coplanar vectors. Velocities of three persons walking in their respective homes situated on different floors are coplanar. They may not be collinear, but they are coplanar. Have you understood this? So if I say for motion in a plane, all vectors are coplanar. For motion in a plane, all vectors, that is the position vector r bar, displacement vector delta r bar, velocity v bar, and acceleration a bar, are always coplanar. Okay? That's why in projectile motion, angular momentum is always directed along z axis. Okay? Fine. Okay, now let us go to linear combinations. Acha, okay. One point I missed. Okay, so two non-collinear vectors are enough to determine a plane, and a vector c bar coplanar with them can always be written as x a bar plus y b bar. Okay, let me write it here. Point 8. For three non-collinear coplanar vectors, we can always have C bar equal to X A bar plus Y B bar, where X and Y are real numbers. Okay. Fine. So this later on gives rise to position vector in 2 dimension. R bar is equal to X I cap plus Y J cap, but that's a different topic. Okay. We will not come to that right now. Acha. Let us now come to linear combinations. Okay. Let us now come to linear combinations. How do we define a linear combination? Simple. We combine the two operations, addition and scalar multiplication. We say let Aj, j is equal to 1, 2, up to n, bar be n vectors. And alpha j be n scalars. We define linear combination. We define linear combination of them as alpha 1 a1 bar plus alpha 2 a2 bar to alpha n an bar. Okay. Next, if at least one of alpha j's is non-zero, we call it non-zero linear combination. Okay, we call it non-zero linear combination. Okay. Now I would like to add a point here, and that point is if the linear combination is a null vector, okay, for some values, for some alpha j, such that at least one of them is non-zero, we call the vectors linearly dependent. Okay, we call the vectors linearly dependent. I'm going to give you an example for linearly dependent and independent vectors. Look here. Okay. Suppose I take a vector a bar as I plus 2j, and suppose I take a vector b bar as 2y plus 3j. Okay. And suppose I take a vector c bar as some k cap. And suppose I take the linear combination of them, let's say x a bar plus y b bar plus z c bar equal to null vector. Okay, equal to null vector. Now look here, is it possible to find x, y, z, at least one of them is non-zero, such that x a bar plus y b bar plus z c bar is a null vector? If yes, we call the vectors linearly dependent, otherwise we have to call them linearly independent. Okay, now you suddenly realize that we are actually going to get a system of linear equations here. Let's solve it. Okay, x a bar plus y b bar plus z c bar equal to 0 bar, it is going to give us the following equations: x plus 2y plus 0z equal to 0. Okay, then 2x plus 3y plus 0 z equal to 0, and then 0 x plus 0 y plus 1 z equal to 0. Did you understand what we did? See, we multiplied the I components by the corresponding coefficients and we got the first equation. Then we multiplied the j components by the corresponding things. So this for a bar it is 2x, for b bar it is 3y, and for c bar it is 0z. And same thing I did for the k component. Fortunately for k only the third thing matter. Okay, so if we write it in the matrix form, we are always going to get a homogeneous system of linear equations. Okay, now look, we will get z equal to 0, right? We will get z equal to 0. And what about the other two? Can we find non-zero xy? See, 0 xy will always give us null vector, but we want at least one of them to be non-zero. Let's explore that. Okay, let's explore that. Okay, so we have x plus 2y equal to 0, and we have 2x plus 3y equal to 0. Now you realize that these are two lines intersecting at origin. Yes or no?
Yes, sir.
So can they have any other point of intersection apart from origin? No. Therefore, the three vectors are linearly independent. This is a very important concept later on in linear algebra, concept of linear dependence and independence. At least one of them is non-zero. We could have called them linearly dependent, but in this case, the vectors that we had chosen, we found out that we cannot find, or it is impossible to have x, y, z, at least one of them to be non-zero for the equality to hold. Which equality? X a bar plus y bar plus z a bar equal to 0 bar. Okay, so they are linearly independent. Fine. Okay, is that clear?
Yes, sir.
Yes, sir.
Okay, now let us see some results pertaining to collinear and coplanar vectors. First, fundamental theorem in plane. If a bar and b bar are if a bar and b bar are non-collinear vectors, they are not along the same line, then any vector r bar coplanar with a bar and b bar can be expressed uniquely as a linear combination of a bar and b bar. That is, there exist unique scalars x and y such that r bar is equal to x a bar plus y b bar. Okay, this is called fundamental theorem in plane, and we can visualize this using parallelogram law. Okay, there are two important words here. The first important word is any. Any vector coplanar with a bar and b bar can be expressed as a combination of a bar and b bar. And the other important word is unique. That means if I select an ordered pair x comma y and get a vector x a bar plus y b bar, I cannot get that vector by any other combination of x and y. Okay, that is the significance of the word unique. Only one. Okay, so if I want to represent a vector, it will always have a unique representation x a bar plus y b bar. Okay, so no two vectors have same representation. Okay, and simultaneously no two ordered pairs x comma y, different ordered pairs, can represent the same vector. Okay. Okay. Next is fundamental theorem in space. Read three-dimensional space. If a bar, b bar and c bar are non-coplanar vectors in space, then any vector r bar can be uniquely expressed as a linear combination of a bar, b bar and c bar. That is, there exist unique scalars x, y, z such that r bar is equal to x bar plus y bar plus z bar. Again, two words are important here. First is any vector r bar in space, and second is unique combination x, y, z. Okay, so if I change x or y or z or any two or all of them, I will never get the same vector again. Secondly, well, it works both ways. So a single vector can never have multiple x, y, z triples for it, and a single triple can never represent multiple vectors. Okay, that is fundamental theorem in space. Have you understood these theorems? Oh, this is important for conceptual understanding, may not be for problem solving as relevant, but you need to know this. There was a question, I don't remember, which had a 4x1 vector. I think in the 17 or 18 edition of the test, IISER aptitude test, there was a question related to this. I think it's 17. Okay, related to this. Okay, fine. So if I go to a 4-dimensional space, then how can I say for r bar xa bar plus yb bar plus zc bar plus wd bar? Okay, and when you generalize this for n-dimensional space, you go on getting more and more interesting results, more and more interesting generalizations, which when brought down to 3 or 2 dimensions, give us the more familiar results. Okay. Yeah, so we can extend this now fundamental theorem in 3-dimensional space by fixing I cap, j cap and k cap. So if I cap, j cap and k cap are 3 unit vectors along x, y and z axes respectively, then any vector r bar can be represented uniquely as r bar equal to a1 I cap plus a2 j cap plus a3 k cap, where a1, a2 and a3 are the coordinates of r bar, or the point we can say. Okay, sometimes we say components also. Okay, do you want me to show the visualization or you have understood it? A1 I cap plus A2 J cap plus A3 K cap. It's clear, right?
Got it, sir.
Got it? Oh, got it. Very good. Okay, now some more useful stuff. Dot product. Definition and working rule. Definition simple. A bar dot B bar is magnitude of A bar, magnitude of B bar, cos of the angle between them, and we know that this angle is never greater than 180 degrees or less than 0 degrees. It always lies in between. Okay? What's the working rule? Working rule says A bar dot B bar is A1 B1, take the product of I components, A2 B2, J components, plus A3 B3. Okay? Product of K components and add. The other name of dot product is scalar product, because the answer is a scalar. Fancier name is inner product. Fancier name is inner product. So there is a topic called vector spaces in linear algebra. Next year you will study that, or in your course for sure. And a special case of vector spaces is inner product spaces. We define an operation of inner product, which is actually the dot product. Okay, that's A bar dot B bar, definition and working too. Do you recall any applications of dot product, not in physics, in mathematics, in 3-dimensional coordinate geometry? Yes. Well, first application of dot product is to find angle between two lines, two vectors of course, two planes, or a line and a plane. We can use dot product as a very effective tool to find the angle between any two entities. Number two, okay, to find projection, okay, to find projection of one vector onto other. I will briefly explain you what projection is later, but these are the two applications in mathematics. In physics we know when the work done, potential energy, power, all of them are dot products. Even electric flux, magnetic flux, etc. Okay, first, a bar dot a bar is magnitude of a bar squared. In some books they print square of vector. I don't think that is correct. Okay, square of a vector is not defined. Square of a vector is not defined. Understood? It's never defined. So it's not mod of, it's not a bar squared. That's never defined. It's mod of a bar squared. A bar dot a bar. Since theta is 0. Right? The angle between the same vector with itself, that angle is 0. So cos theta 1, a bar dot a bar is mod a bar squared. Have you understood this?
Yes, sir.
Okay, so see, look, a bar squared doesn't make sense. A bar squared does not make any sense. Similarly, 3 dot a bar also does not make any sense. And 3 cross a bar also, because 3 is not a vector. Okay, so just say 3 a bar. Okay. Other, yeah, a bar dot b bar is projection of a bar on b bar multiplied by b bar. Now let me explain this a bit. Suppose we take a line along b bar. Okay, suppose we take a line along b bar. Suppose we take a line along b bar. Okay, this is b bar. And suppose I take a vector. Now for convenience I'm showing it non-collinear with b bar, but I can very well show it to be collinear. Okay, suppose this is a bar. So what I do is I drop a perpendicular from a bar on the line, from the tip of a bar on the line parallel to b bar. Okay, this is what I do. And suppose I call this angle as theta. Let us say I call this point P, this point Q, this is the right angle, and suppose this point is R. Then I come to know that PQ is PR cos theta, or specifically PQ bar is equal to PR bar into cos theta. Okay, PR bar into cos theta. So I can also write this as A bar into 1 into cos theta. I'm not going to change anything. Okay, so I just multiplied it by 1, and in order to get it as a dot product, I write 1 as okay, let me put it in this way now. PQ bar is PR bar cos theta, or A bar into 1 into cos theta. Therefore magnitude of PQ bar, okay, I can write it as magnitude of A bar, magnitude of 1, magnitude of cos theta, okay, or PQ. Now this is a directed segment now. It is A bar dot B cap. Or okay, let us make one more step here. Okay, I can write it as mod of A bar dot B cap. Now how to find B cap, how to find a vector parallel to, unit vector parallel to any vector? By dividing the vector by its own magnitude. You know this, right? This is the standard result. Everybody knows the result? Yes? Okay, so that is called projection. So PQ is the projection of PR, or A bar on B bar. So A bar dot B bar is projection of A bar on B bar into magnitude of B bar. You can remember this result. and B bar dot A cap will be projection of B bar on A bar. Okay, that is one use of dot product. Okay, next is cross product. You know this figure from H.C. Verma. How do we define cross product of A bar and B bar? Magnitude of the first, magnitude of the second, sine of the angle between them into a unit vector perpendicular to the plane of A bar and bar. To find the direction of the unit vector and cap, we take the palm of our right hand, we place its fingers along the first vector, we curl the fingers along the second vector, the direction of the thumb points the direction of cap or A bar cross B bar. What is the working rule? Working rule is A bar cross B bar is determinant IJK A1, A2, A3, B1, B2, B3. We will use this in scalar triple product, which is following. Okay, cross product clear, definition and working rule. Of course, we have many applications of cross product in physics, right? We have many applications of cross product in physics, like torque, moment of a force. Okay, then what else? Lorentz force, that is also cross product, isn't it? Okay. We will see the applications of cross product soon in mathematics. Okay, let's first see some properties. First, it is anti-commutative. A bar cross B bar is equal to negative of B bar cross A bar. Okay, we call it anti-commutative. A bar cross A bar is a null vector, or we can also say that for two vectors. Oh, okay, let me put it in this way. I think I have included them here. Let me check. Okay, I've included them here. Okay, fine. So I won't rewrite the applications. Okay, I won't rewrite the applications. Fine. A bar cross A bar is a null vector. Distributive property of cross product over vector addition. A bar cross B bar plus C bar is equal to A bar cross B bar plus A bar cross C bar. And this is also a property. Like matrices, we have left distributive property and right distributive property. Okay, those are the properties. See, there are many other properties also, but these are the basic ones. Okay, using them we can get some results. Applications of cross product in mathematics. Two non-zero vectors A bar and B bar are collinear if and only if their cross product is zero, a null vector. Now, if and only if is a biconditional statement. Are you people aware of biconditional statements? Right, so and truth value of a biconditional statement? When both have same truth value. So when P is true, Q must be true. When P is false, Q must be false. That is the logic behind biconditional statement. See, that means if we have two non-zero vectors which are collinear, then their cross product must be zero. Conversely, if A bar cross B bar is a null vector with none of them being non-zero vectors, then they must be collinear. Okay, so it's P implies Q and Q implies P. Okay, that's the mathematical logic or reasoning notation. In NCERT, this chapter is there in the 11th standard mathematics. Okay, fine. So two non-zero vectors are collinear if and only if their cross product is a null vector. Okay, so that's one application. Understood, or shall I explain it again? Okay, second. Area of the parallelogram whose adjacent sides are represented by the vectors OA bar equal to A bar and OB bar equal to B bar is magnitude of A bar cross B bar. And remember, in Gauss law, which law? In Gauss law of electrostatics, we require vector area. Remember that? We require vector area. So how is that vector area defined? That vector area is defined as Okay, let's say we have a small parallelogram there. Okay, we have a small parallelogram there. So let's say this is the area, this is A bar, this is B bar. Then what will be A bar? A bar is actually A bar cross B bar. So that is why we say that area vector is normal to the plane. Okay, area vector is perpendicular to the plane of area. It's 90 degrees. Okay, vector area. So how to determine the direction? Pick any two vectors. Let the area be made up of parallelograms. Let two edges represent A bar and B bar. Take the cross product, you will get both the magnitude and the direction of the area. Okay. What will be the area of the triangle OAB then? Half of it. Okay. Half of it. Okay. Fine. What is the unit vector perpendicular to the plane of A bar and B bar? See, we know that cross product is perpendicular. So what we say is find the cross product, divide it by its own magnitude. You will get a unit vector. And there can be a vector normal, well, in the other direction also, so say plus or minus. Have you understood this? Okay. Fine. Now let us go to scalar triple product. Okay, scalar triple product. The word scalar means the product is going to be a scalar quantity. Triple means we require three vectors. Okay, definition. A bar dot excuse me, A bar dot B bar cross C bar. Okay, that is the definition. First you find the cross product of a B bar and C bar, and then you take its dot product with A bar. What is the working rule? Look, the working rule is the determinant A1, A2, A3, B1, B2, B3, C1, C2, C3. Now this is typical. Why? There's nothing unusual here. Look, if you were to define B bar cross C bar or find B bar cross C bar as a determinant, you would write IJK here. But now we have got A bar dot that. How do we take the dot product? We take the pairwise products of I components, J components, K components and add. That's exactly what we're going to do. So the working rule is A bar dot B bar cross C bar equal to determinant A1, A2, A3, B1, B2, B3, C1, C2, C3. Is that clear? Yes? Now because it is a determinant, all properties of determinants apply to dot product also, scalar triple product also. Okay? I think I had told you this when we are discussing determinants. All properties of determinants apply to scalar triple product. Okay, all properties of determinants apply to scalar triple product. Typically, look, when we discussed coplanar vectors, did I not say that C bar is equal to H A bar plus Y B bar? Yes. Now, look, if we take such a combination, if we take C bar as X A bar plus Y B bar, there is no need to even calculate this. I know that it is going to be 0. Why? Because the third row here of the determinant can be made 0. How? Do the operation R3 minus X R1. What will you get? You will get something, and then do the operation R3 minus Y times R2. You will get 0, 0, 0 there. Right? And those are properties of determinants that we have taken. Okay? So we can use properties of determinants to solve scalar triple product problems. Okay, fine. Property 1. Cyclic change in the scalar triple product does not change its value. Meaning A bar dot B bar cross C bar. Now let us bring in the cyclic change. Okay, that means let B bar be replaced by C bar. Let C bar be replaced by A bar. Let A bar be replaced by B bar. This is as good as interchanging rows twice. Okay, so it's not going to change the value. Same thing. Replace B bar by C bar. Replace C bar by A bar. Replace A bar by B. Cyclic change doesn't make any difference in the value of the scalar triple product. Okay. Yeah. Second thing is locations of the dot and cross are also immaterial. Locations of dot and cross are interchangeable. Okay, are interchangeable. You can verify this property also or prove it using properties of determinants. Now, do you people know what is a parallelepiped? Do you know that? Yes?
No.
Okay. So parallelepiped is like a box, but whose faces are parallelograms. Whose faces are parallelograms. Our typical box has rectangular faces, correct? So if we have a box, okay, let me give you an example. Okay, I think this is something that you can understand. How many of you know the shear stress, the concept of shear force, shear stress? You know it, right?
Yes, sir.
So suppose we take a bread loaf, and we stretch it. Okay, let me draw the figure first to help you visualize the concept. See, this is our box. Okay, suppose this is our box. Okay, suppose this is our box. And suppose we apply some force to it. Okay, some tangential force. So what will happen? It will shift, right? Well, this is an exaggeration, but this is indeed what we expect to happen. These ends will come forward and those ends will also shift or get displaced in the appropriate directions. Right? Yes. Now you see that these faces cease to be rectangles, but it's still a box, still looks like a box, right? This still looks like a box, so that is called a parallelepiped. Okay, so that is called a parallelepiped. What do we call it? Parallelepiped. Okay, let a parallel. Shift it like that. Okay, and we can also move it in this direction. Okay, anyway, so as long as the faces are parallelograms, we will get a parallelepiped. Okay, now if we have a parallelepiped whose adjacent sides are represented by A bar, B bar and C bar, okay, whose adjacent sides are represented by A bar, B bar and C bar, let us say for example, suppose this side is A bar. Suppose this side is A bar and suppose this side is B bar. we already know that A bar cross B bar is going to represent area, right? We already know that A bar cross B bar is going to represent this area. So if we take its dot product with this, that is as good as the height. Okay, that is as good as the height. Then the scalar triple product of that, all of them, is going to give us the volume. Okay, what is it going to give us? It's going to give us the volume. Okay, the volume is A bar dot B bar cross C bar. Now let me help you visualize this, and I have a nice thing, an animation for that. Okay. Now do you people know tetrahedron or tetrahedral structure? Methane has a tetrahedral structure. So the carbon atom sits at the center, and the 4 hydrogen atoms, they are at vertices of a tetrahedron. Tetra means 4. What does tetra mean? Tetra means 4. Okay, hedron means, I forgot the name. It's a Greek word. Hedron, I guess, means points or faces. Anyway, that is irrelevant. So what is a tetrahedron? Tetrahedron is a 3-dimensional object which has 4 vertices. So if you imagine a triangle on your desk, any triangle, and if you take a point above that and join the 3 vertices of the triangle with that point, the figure that you will get is a tetrahedron. Look here. Suppose this is your desk and you take 3 points on it and you form a triangle. Lift your hand from the surface, take a point in space and join all the points with that. You are going to get a tetrahedron. Okay, and the volume of the tetrahedron is given by 1/6 into A bar dot B bar cross C bar. Now what are A bar, B bar and C bar? A bar, B bar and C bar are again the coterminus or adjacent edges of the tetrahedron. For example, suppose this is A bar, edge A bar. Suppose this is edge B bar. And suppose this is C bar. Okay, suppose this is C bar. Edge A bar. So edges A bar and B bar are in your plane and C bar is not. It's 1/6 of that. And usually we take the mod considering volume to be a non-negative entity. Okay, so volume of the tetrahedron is equal to 1/6 of the original scalar triple product. Let me show you a visual proof of this. Okay. So first of all, I want all of you to take a look at this particular object. Okay, now this object consists of 6 faces. Opposite faces are equal, but they are not rectangles, they are parallelograms. You can see this face is a parallelogram, not a rectangle. This face is also not a rectangle, but a parallelogram, and so is the top face. Okay, so this particular 3D object is called a it's called a parallelepiped. Now, because one of its vertices is at the origin, suppose you take 3 vectors pointing along 3 different, 3 different vertices, A bar, A, B, C, you will get 3 vectors, and the volume of the the volume of the parallelepiped, that means if you take water and pour it inside, how much water will fit in? It will be given by the cross product of 3 vectors. Which 3 vectors? The vector from origin to A, origin to B and origin to C. That scalar triple product, if you find, that will give us the volume of the substance that you can fill in here. Have you got the idea of what parallelepiped is?
Yes, sir.
Now parallelepiped with every angle 90, it will become a rectangular box. Okay, it will become a rectangular box. Okay, so this is a parallelepiped. Now look, It's the same parallelepiped that we see here, that you see here, and its three faces that are visible to us, that are in front of us, are shown in the red, the blue and the green color. There are other three faces which are not directly visible here. Okay, now what I'm going to do is I'm going to bring this E. Okay, now see what is happening. This was our parallelepiped. It has now split itself into 6 objects. The description of these 6 objects is that each object has 4 vertices and 3 triangular faces. There are 3 points in the plane and the 4th point is not on the plane. So we are getting 6 tetrahedra. We are getting 6 tetrahedra. All of them have same volume, which is equal to a sixth of the original tetrahedron. It's like fitting a puzzle. Okay, it's like fitting a puzzle. So if we take the 2 green tetrahedra, the 2 blue tetrahedra and the 2 red tetrahedra, all of them will have the same volume, and each one of them will have volume equal to a sixth of the original parallelepiped. Okay, so that's it. And black point D, let's try to make it a box if I can. Okay, A, B, C is that. Yeah, now it looks like a box, right? It looks like a box. So this box gets split into 6. Now see, they are not pyramids actually, per se. They are not pyramids, because pyramids have square base. These have triangular base. Okay? Fine. So that is a tetrahedron. Okay, 1/6 of the volume of parallelepiped. Okay, now there are some other properties also. Other properties. Okay, one more thing. Because scalar triple product gives volume of a box-like object. Like parallelepiped is after all like a box. So because scalar triple product gives volume of the box, so we sometimes call scalar triple product as box product. What do we call it? Box product. What is the reason? Reason is it gives us a volume of a box. Okay, it gives us volume of a box. So we call it box product. And not only that, we actually use box brackets to represent scalar triple product. Look here. When I say box A bar, B bar, C bar, when I say box A bar, B bar, C bar, I actually mean A bar dot bracket B bar cross C bar. Okay, that's us. Well, that is box product. Okay. Now 2 interesting properties. Second one is more interesting, I would say. The box product of A bar, B bar, C bar multiplied with the box product of U bar, V bar, W bar is the determinant A bar dot U bar, B bar dot U bar, C bar dot U bar, A bar dot B bar, B bar dot B bar, C bar dot B bar, and A bar dot W bar, B bar dot W bar, C bar dot W. Remember that derivative of a determinant expression which consisted of 3 determinants every time we differentiate one row? Something similar to that. Okay? Not exactly 3 determinants, but you take dot product of every vector in the first to every vector in the second. It's like it's as good as multiplying 2 matrices, if you see. Okay? Fine. The other property is A bar cross B bar dot C bar cross D bar is determinant A bar C bar, B bar C bar, A bar dot D bar, B bar dot D. Okay? You may take 3 vectors or 4 vectors of your choice and prove. Take A bar, B bar, C bar and D bar of your choice and verify these 2 properties. Can you guys do it? Yes, of course, right? Please don't take some simple vectors, okay? Take some complicated vectors. Preferably having non-zero IJK components, and do that. Last part is vector triple product. Okay, last part is vector triple product. The definition is A bar cross B bar cross C bar is A bar dot C bar B bar minus A bar dot B bar C bar. Now you have to learn this. Okay, please learn it. because you don't have time to derive it. Okay, learn it by heart. A bar cross B bar cross C bar is A bar dot C bar B bar minus A bar dot B bar. You can prove it by assuming A bar to be A1, A2, A3, B bar to be B1, B2, B3 and C bar to be C1, C2, C3. Now I want to tell you one more thing. A bar cross B bar cross C bar is always coplanar with B bar and C bar. Reason is simple. B bar cross C bar is perpendicular to B bar and perpendicular to C bar. Correct? That's cross product's property. It is perpendicular to the parent vectors. Therefore, A bar cross B bar cross C bar will be perpendicular to A bar, and more importantly it will be perpendicular to B bar cross C bar, and therefore coplanar with B bar. Make sense? Understood this? So it is as good as this, x B bar minus y C bar. That's what I'm saying. This is x and this is y. Do you get this, or shall I explain it again? Yes, understood?
Yes, sir.
Okay. 3D coordinate geometry using vectors. Now there is a reason why I have written using vectors. You can study 3D coordinate geometry independently, not involving vectors. And of course you are still going to get the same results. But if you use vectors, the concepts of vector addition, magnitude of vector, dot product, cross product, scalar triple product, projection of vector, it is going to be of much use. Okay, so remember, everything that we have discussed in vectors will be required here. Let us begin. First, the basics. The three-dimensional space consists of three mutually perpendicular axes, and we use a right-handed system. Okay, we use a right-handed system, that is I cross j is equal to k. Okay, now although we say we use a right-handed system, to actually represent it we use the left hand. Okay, why then it is meant or called a right-handed system? It is called a right-handed system because if from x-axis to y-axis, positive x to positive y, if we go in the anti-clockwise direction, or if we take the right hand, curl our fingers, if the direction of the fingers is from positive x to positive y in the first quadrant, then the thumb is going to give us the direction of the z axis. Have you got this idea, right-handed system? Okay, yes, right. That is basically the rule that we use to find the cross product's direction, right hand. Okay. Now the whole of the three-dimensional space gets divided into 8 octants. Okay, the whole of the three-dimensional space gets divided into 8 octants. Okay, now what are these 8 octants? We have 4 quadrants already in the xy plane into 2. Okay, so the portion above the first quadrant is called first octant. The portion above the second quadrant is called second octant. Above the third quadrant is called third octant. Above the fourth quadrant is called fourth octant. And in all these first 4 octants, the sign of the z coordinate is positive. Okay, the sign of the z coordinate is positive, and everywhere else we have the same. First quadrant positive positive, second quadrant negative positive, third quadrant negative negative, fourth quadrant positive negative. Okay. Now if we go to first quadrant and go below that where we have the negative z axis thing, so there you will have same sequence. Fifth octant is below the first octant, sixth octant is below the second octant, then something which we cannot see because of these planes, that is the thing in the third, well, below the third quadrant is our seventh octant, and this is our fourth octant that is below our fourth quadrant. Have you understood this? 8 octants. Then we have three axes x, y, z, which are mutually perpendicular. Three mutually perpendicular axes and three coordinate planes. Formed by taking two axes at a time. Okay, two axes at a time. XY plane, YZ plane and ZX plane. Now let us go to coordinates. So what are coordinates? Every point P in the three-dimensional space is associated with a unique ordered triple of coordinates x, y, z. Okay, now what does that mean? That means no two points can have all three coordinates same. Okay, no two points can have the same coordinates, right? And the same point cannot have two different coordinates system or two different coordinates x, y, z. Okay, only one. Fine. I'll tell you how to determine those coordinates later. First, let us consider some special situations. If we consider points on the axes, let us first start with x-axis. Okay. If a point is on x-axis, okay, if our point is on x-axis, it is clearly going to have its y coordinate 0 and its z coordinate 0. Same logic applies. Okay. So look at these 2 points, 10, 0, 0 and negative 3, 0, 0. Negative 3 is this red dot, this blue dot on the x-axis. Okay. So if this number is positive, then it is on the positive part. If it is negative, then it is, we say, on the other side of the YZ plane. And if it is 0, then it is origin. Okay. Similarly, we can extend this discussion to a point on y-axis whose x and z coordinates will always be 0. Now, if this number here is positive, it will be on this side of the zx plane, right? And if y coordinate is negative, it will be on the other side of the zx plane. Same thing if we carry out for z-axis, all points on z-axis have their x coordinate 0, y coordinate 0. If the z coordinate is positive, it means the point is above the xy plane. If it is negative, then the point is below the xy plane. 6, 0, 0, 0, 0, negative 4 are examples of points on z-axis and their coordinates. 0, 8, 0, 0, negative 3, 0. This blue dot here are examples of points on y-axis. This part is clear? Oh yeah. Yeah, correct. Thank you. 0, 0, 6. Yeah. Okay, now let us consider points which are on coordinate planes. First, let us consider the xy plane, and you can see that z-axis is perpendicular to that. If we have a point on xy plane, then its z coordinate will be 0. Okay, by default its z coordinate will be 0. And how do we determine the x and y coordinates? That's the same procedure that we follow. We drop a perpendicular from that point to x-axis. Here the number is 4, so its x coordinate will be 4. And here we drop a perpendicular on y-axis, we get its y coordinate as 6. Okay, so that is our 2D. The whole of our 2D is here, right? The whole of our two-dimensional coordinate geometry is here. The whole of 2D geometry, whatever activities you have, conics, anything, is in xy plane. Well, we can take it in any plane we want, but to simplify things, we always take it on xy plane. Okay? Next, if we take the yz plane, okay, if we take the yz plane, then all points on it are going to have x coordinate 0, right? X coordinate 0. And how do we determine its y and z coordinates? Simple. Drop a perpendicular on y-axis. Wherever it meets the y-axis, that is going to be your y coordinate. This time it is negative 4. And drop a perpendicular on z-axis, you are going to get its z coordinate, and because this is, well, according to its position, its z coordinate should be positive. Okay, fine. Then finally zx plane, which coordinate will be 0 here? Obviously y coordinate will be 0. Okay, y coordinate will be 0. And how do we find the coordinates? It's, well, again simple. Just draw perpendiculars on the respective axes. Just draw perpendiculars on the respective axes, you'll get the corresponding coordinates. So if we drop a perpendicular on x-axis, this number is negative 10. If you can't see, it's negative 10, and this number is negative 3. So the coordinates are negative 10, comma 0, comma negative 10. Is this clear? Simple. Okay. Yes. Now let us come to the question of determining coordinates of a point in space. Okay. So let's consider a point here. The first thing that I'm going to do is, I'm going to drop a perpendicular from that point on the xy plane, and I'm going to call its point of intersection with xy plane as n. Okay, as n. After that, what I'm going to do is, I'm going to drop a perpendicular from m on x-axis. I'm going to call it n, and whatever number I see, I will call that as its x-coordinate. Okay, I will call that point as its x-coordinate, comma. Now from m, I'm going to drop a perpendicular on y-axis. Whatever number I see there, that is going to be its y-coordinate, so 4. Okay. Now how can I determine z-coordinate? To determine the z-coordinate, first I will consider the relative position of the point P with respect to xy plane. If it is above the xy plane, its z-coordinate will be positive. If it is on the xy plane, its z-coordinate will be 0. If it is below the xy plane, its z-coordinate will be negative. In the picture here, the point happens to be above the xy plane, so its z-coordinate will be positive. Its z-coordinate will be positive. And how are we going to find its value? The length of PM, that itself will be the z-coordinate of that particular point. So that coordinate will be 5. Tell me whether you understood this. Okay, let me call this point as Q. So Mn is the x-coordinate, MQ is the y-coordinate, and MP is the z-coordinate. Now these are directed distances, okay? These are directed distances. Have you understood this? Okay, now let us also try to develop the position vector here. Okay, let us also try to develop position vector here. So suppose I draw ON bar. Okay, suppose I draw ON bar. Can I say that ON bar is 5 I cap? Yes, I can say that ON bar is 5 I cap. Okay, now suppose I draw OQ bar. Can I say that OQ bar is 4J cap? Yes, I can say that OQ bar is 4J cap. Because it is along positive y-axis, this has to be 4J cap. Okay, now when I add these two, I'm going to get OM bar. Am I right? When I add ON bar and OQ bar, by parallelogram law of vector addition, I'm going to get OM bar. Correct? Now when I add OM bar to MP bar, okay, MP bar, MP bar is 5K cap. MP bar is 5K cap. And if I consider OM bar plus MP bar, by triangle law, I will get OP bar, that is the position vector of point P. Okay, we usually denote it by R bar. Is that clear? By parallelogram law and triangle law of vector addition, we get the coordinates of P. So always remember to drop a perpendicular on that particular xy plane. Then the coordinates of that foot on the xy plane, the way we determine it in 2D, Those will be x and y coordinates of our point. Now measure the distance of P from the xy plane, that will be z coordinate if it is above, positive, on, 0, below, negative. Okay? Fine. Let's now discuss some more preliminaries. Distance of point P from coordinate planes. Well, actually that is the extension of our procedure of determining the coordinates. If we take the xy plane, then its distance from the xy plane is going to be mod of its z coordinate. Distance from yz plane is going to be mod of x coordinate, and the distance of the point from the zx plane is going to be mod of its y coordinate. Okay, this does not need any further explanation, right? I have drawn the figure also for your better visualization. Okay, distance of the point P from the axis. Okay, now this is something which you may find a bit tricky, but it's very simple. Okay, distance of point P from the axis. Now suppose I ask you, how far is point P from x-axis? Okay, how far is point P from x-axis? Now to do that, to help you visualize this, I'm going to ask you to imagine this particular rectangle. Okay, this particular rectangle, consider rectangle PMRL. It is a rectangle. Do you agree? It is a rectangle. Yes, it's a rectangle. LPMR or PMR. It's a rectangle. Okay. Is this rectangle parallel to YZ plane? Yes, it's parallel to YZ plane. Exactly. Which means x-axis is perpendicular to our rectangle. Which means if I take any point on the rectangle and join it with the point of intersection with x-axis, what will I expect? That is actually going to be a 90-degree angle there. Some people find it hard to believe. Which angle will be 90? Let me be specific about it. Angle PRX is going to be 90 degrees. Are you convinced or not? Or have you understood it or not? Don't get convinced because I am saying it. You understood it, right? Exactly, very good. Angle PRX is 90 degrees. So PR is actually the distance now. And what is its distance? It's root of PL squared plus PM squared. What is PL? Distance along y-axis. What is PM? Distance along z-axis. So if it is x-axis, then it is root of y squared plus z squared. And similarly, you can develop expressions for the distance of the point P from y-axis, root x squared plus z squared, from z-axis, root x squared plus y squared. I will not believe actually. Do you remember this theorem that we had discussed? Perpendicular axis theorem in rotational motion? Yes. And there we have directly or indirectly used this fact that distance from z-axis is actually root of x squared plus y squared. We actually used it. Are you aware of it or not? I don't know. But in perpendicular axis theorem, agreed that it applies only to planar bodies or lamina. We have actually used that. Distance from z-axis is root of x squared plus y squared. Okay, we used that. And here is a proof. For x-axis, you can similarly prove it for y and z. Okay, fine. So that is with coordinates. Now let us try to discuss directions. Okay. The first is direction angles, direction cosines, and direction ratios of a vector. Okay, of a vector. Now here we assume that our vector is a free vector. We assume that our vector is a free vector, meaning its initial point can be anywhere in space. We fix it to origin. We fix it to origin. So suppose I say my vector is a1 I cap plus a2 j cap plus a3 k cap. How do we define its direction angles? Theta x is the angle between A bar and positive x-axis. Theta y is the angle between A bar and positive y-axis. And theta z is the angle between A bar and positive z-axis. Okay? So for vector, we only consider the angles made by the vector with positive directions of the coordinate axis. For line, the situation is different. Okay? Fine. So for A bar, these are the direction angles theta x, theta y, and theta z. Any idea how do we find theta x, theta y, and theta z? If don't, listen to me. Cos of theta x is equal to, now look here, what is theta x? Theta x is the angle between what? A bar and x-axis. Okay, so I may say here that let me take a unit vector along A bar, that's A cap, and let me take its dot product with I cap. Now why does this work? Look, how have we defined dot product yesterday? Or well, whenever we discuss the theory of vectors. Magnitude of A cap, magnitude of I cap into cos of theta x. But these two being unit vectors, A cap and I cap, their magnitudes will be 1. So cos theta x, cos theta x. So cos theta x is A cap dot I cap. Have you followed this?
Yes, sir.
Yes, definitely. Okay. Yeah. And then similarly, can you write cos theta y? A cap dot j cap, and cos theta z will be what? A cap dot k cap. Okay. These direction angles, okay, theta x, theta y, theta z, their cosines are called direction cosines. Okay. We usually use the letters L and N for them, and this can also be proved, but I'm not going to prove, that Li plus Mj plus Nk is actually A cap. Okay, you can establish that. I'm not going to prove that for you. So it is a unit vector. Now what are direction ratios? Any three numbers which are proportional to direction cosines are called direction ratios. Okay. A, B, C are direction ratios, DRs, if A is proportional to L, B is proportional to M, and C is proportional to N, A, B, C belong to R minus 0. Okay. Well, all three of them cannot be simultaneously 0. Okay. If two of them are 0, then it is going to be along some axis, right? And if any one of them is 0, then it is going to be in some plane or parallel to the plane. Okay, understood? Direction, cosines, direction angles, okay. Now when it comes to a line has two sets of direction angles. Okay. I just write that. A line has two sets of direction angles. Because A cap and A bar and negative A bar are both along the line. Therefore, okay, or therefore, if theta x, theta y, theta z are direction angles of A bar, then pi minus theta x, pi minus theta y, pi minus theta z are direction angles of negative A bar. Okay, so LMN and negative L, negative M, negative N, they both are direction cosines of line. Tell me whether you understood this or not. Understood, right? And we have used actually cos of pi minus theta as negative cos theta in that printing mistake MCQ, right? Okay. That's about line. Now let us discuss the equations of lines in 3 dimensions. The first form that we are going to see requires us to know a point and direction. So this is analogous to slope point form. This is analogous to slope point form, and here we are, see, because the point is already there, the vector direction indicator is going to play the role of slope. Okay, here we use the concept of collinear vectors. Okay, so what we say is, suppose L is our line, A is a known point on the line, P is a variable point on the line, and B bar is the direction indicator. B bar is the direction indicator. So what we say is AP bar is collinear with B bar. But what is AP bar? R bar minus A bar, right? For unknown point we always use R bar. That's lambda B bar. So R bar is equal to A bar plus lambda B bar. That is the vector equation of line. As lambda's value changes, we go on getting different points. If lambda is 0, then we get point A. Have you understood this?
Yes, sir.
Now if this position vector of A, suppose it has coordinates x1, y1, z1, and suppose the direction indicator has components A, B, C, those are direction ratios of the line, then we get x minus x1 upon A, y minus y1 upon B, z minus z1 upon C. This is called symmetric form of equation of line. This is called vector form, and if we assume that every ratio is equal to lambda, then x becomes x1 plus A lambda, y becomes y1 plus B lambda, z becomes z1 plus C lambda. These three equations are called as Cartesian equations or parametric form. Lambda is the parameter. The name is not important. What's important is the way we have got them and how we interpret them. Is it clear?
Yes, sir.
Yes? Okay. Now let us discuss equation of line through 2 points analogous to 2-point form. So here we almost use the same thing. Okay, we almost use the same thing which we used earlier, but here the situation is a bit different because we do not know the direction vector, direction indicator, but we can easily determine it because we know 2 points on the line. So suppose L is the line, A, B are points, known points on the line. Okay, so what can serve as the direction indicator? A, B bar. So here B bar does not mean direction indicator, okay? Here B bar means position vector. That's what's shown in the figure. OA bar is small a bar, OB bar is small b bar. So direction indicator is B bar minus A bar. So what will be the equation? R bar equal to A bar plus lambda times direction indicator. Or it will be A bar plus lambda times B bar minus A bar. Writing it in fancier notation, it will be 1 minus lambda A bar plus lambda B bar. Lambda is a real number. I hope you will be able to convert this equation into scalar form. If not, tell me, I will do it for you. Shall I do it? Okay, suppose A has coordinates x1, y1, z1, and suppose B has coordinates x2, y2, z2. Okay, x2, y2, z2. Then AB bar will be x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. Right? So we will get x minus x1 upon x2 minus x1, y minus y1 upon y2 minus y1, z minus z1 upon z2 minus z1 equal to lambda. Okay, those are the scalar equations. If you take first three, they show that if you include the last one, then it becomes parametric. Okay? Any doubt?
No, sir.
Okay, great. Distance of a point on a line. Now this situation requires us to know projection, the concept of projection. Okay? Now I'm only going to write the formula in the vector form. You can get it in the scalar form. Okay? So what do we have here? We have a line L whose equation is r bar equal to a bar plus lambda b bar. A bar is position vector of a point on the line. B bar direction indicator. Okay, B bar is here, L is the line, and P is a point not on the line. And suppose its position vector is alpha bar. M is the foot. PM is to be calculated, distance. Okay, using right triangle property, can I say that PM is AP squared minus AM squared or MA squared? Yes or no?
Yes, sir.
Now what will be AP? AP will be mod of alpha bar minus A bar. Correct? Mod of alpha bar minus A bar, because AP bar is alpha bar minus A bar. Correct? Final minus initial. Okay. Now how are we going to find MA? MA is AP cos theta. Right? Well, we only need the length, so it doesn't matter really whether we consider MA or AM. Okay. So if this angle is theta, it's AP cos theta. Now look how I'm going to write it. Pay attention. I'm going to say AP bar magnitude, P cap magnitude cos theta, or it is AP bar dot B cap. So we basically will require the unit vector along the line, which will also give us the direction cosines of the line. Is it clear? How cos theta came there? It's clear, right? See, it's very essential to know why can we not consider any other unit vector here? Because we eventually want to reach the dot product definition. And for that dot product definition, theta has to be the angle between the two vectors whose dot product we're interested in finding. So it is AP bar and AM bar, right? For AM bar, we just require the unit vector. Have you understood this? This should be your approach given a problem. Okay, given a problem, this should be your approach. Is it clear? There is an alternative to this also. We have to find the coordinates of M in that case. So we use the parametric form of line L. So M will be then represented by some parameter lambda, and then we use the fact that PM bar is perpendicular to B bar, use dot product equal to 0, get lambda, get M, find distance PM. But this process that I have explained you using right triangle, that entirely bypasses the procedure of finding coordinates of M. There is no need to find coordinates of M. Okay, we can directly find the distance using projections. So that could be an alternative method to find the distance PM. Okay. Yeah. Now we are going to discuss a situation which doesn't have a good analog in two-dimensional coordinate geometry, and that is skew lines. And to understand the concept of skew lines and to find the distance between them, the least distance between them, I'm going to ask you to imagine this. Suppose we have a river. Okay, suppose we have a river and there is a bridge across the river. I have assumed that the center line of the bridge has equation r bar equal to a2 bar plus mu b2 bar, and the river has, it's a line, it has equation r bar equal to a1 bar plus lambda b1 bar. And when I say distance between the two lines, see, these lines are not coplanar. In 3D, if lines are not coplanar, they are called skew. Okay, they are called skew lines. And the formula here applies to skew lines and intersecting lines. The intersecting lines can never be skew. Okay? Fine. Now this formula is not applicable to parallel lines. The reason is evident, we will see. Okay? The formula here applies to skew lines and intersecting lines. It gives us the least distance. It gives us the least distance. Okay? It's not just the distance, the least distance, smallest. The least distance between the lines. Now when we talk about least distance, we are interested in a direction which will be perpendicular to both these lines, isn't it? It will be perpendicular to both these lines. So it will be not only perpendicular to the bridge, but it will also be perpendicular to the river, right? So how can such a situation be represented using vectors? Any suggestions? You can do it, you can prove it. The distance is given by a2 bar minus a1 bar. Okay, a2 bar minus a1 bar dot b1 bar cross b2 bar upon magnitude of b1 bar cross b2 bar. So please try to understand, what does b1 bar cross b2 bar give? b1 bar cross b2 bar, this thing gives us a vector which is perpendicular to river line as well as perpendicular to the bridge line, right? So at least we've got the direction there, perpendicular to river line and bridge line, correct? And when I divide it by its own magnitude, I'm going to get a unit vector, and my job is done now. I take one point on one line, the other point on the other line, and I just take its projection on that. I'll get the least distance between the two lines. Got it?
Yes, sir.
Right, okay. Now if the lines are intersecting, then this scalar triple product will obviously be equal to 0. Okay? Fine. Yes. Now the last part on lines, distance between parallel lines. Okay? Suppose that we have L1 whose equation is, let's say, r bar equal to a1 bar plus lambda b bar, and suppose this is r bar equal to a2 bar sorry plus lambda b bar. Lines are parallel, so the direction vector can be considered the same for both of them. Okay, maybe I should use a different parameter here. Okay, any suggestions for the distance between two parallel lines? How can we find that? How will you approach such a problem when given? Find the distance between parallel lines. Can you come up with any situation like that? It's simple. Look, suppose this point is A1 or A1 bar, and suppose this point is A2 bar. So I can view this problem as length of perpendicular from A1 on what? L2. Okay, so I can use the same formula which I used earlier. What is that formula? It is okay, it's this. Let me complete the right triangle. So what will it be? It will be root of A1 A2 squared minus, suppose this is foot m, minus A2m squared. And now you can refer to the length of perpendicular formula from a point, okay, to find the final answer. Is that clear? Yes or no?
Yes, sir.
But there is one more thing that you may not have noticed. This is fine. This is one way to do it. Okay, this is one way to do it. But there is another better way to do it. Okay, and what is that way? Look, if I call this angle as theta, what distance do I want? I want A1m. Can I say that it is A1 A2 sine theta? Yes, no. Can I say that A1m is equal to A1 A2, that's the hypotenuse, into sine theta? Yes. Now that sine theta should immediately ring some bells in your head. Sine theta deals with cross product, right? So it will be magnitude of A1 A2 bar cross B cap. Tell me if you understood that.
Yes, sir.
Danish, Rajat, have you understood? Okay, fine. So this is theta. Okay, so you can also take this formula here. Just find the distance A1 A2 bar cross B cap. Okay, fine. So that completes the theory of lines and basic 3D geometry. Let us now go to planes. Yes, let's now revise planes. Plane is a flat surface. Okay, plane is a flat surface which extends to infinity. Okay, which extends to infinity along any two non-parallel lines. Correct? So it doesn't have a finite surface area, right? Just like a line doesn't have a finite length, a plane doesn't have finite surface area. Okay. Now for a line, two non-collinear points are enough, or one point and direction ratios are enough. For a plane, what are the requirements? Okay. First, if we have two intersecting lines, they determine a unique plane. But you can understand that x and y axis that determine the xy plane, correct? Two parallel lines also determine one single plane, just like 2 points determine one single line. Third, one line and 1 point not on the line, they also uniquely determine a plane, and the answer is here. 3 non-collinear points always determine a plane, so the basic requirement for a plane is that we have only any three non-collinear points. So a triangle is a plane basically. Okay, and all other things follow. A triangle is a plane. Okay? So any three non-collinear points are going to determine a plane, and for the third situation, if this is the line, take any 2 points on the line and take the third point here. Okay, that determines the plane. Understood? So technically, given any of these situations, should be able to determine the equation of the plane. Same thing with two parallel lines. Pick 3 points on the two lines, any two on one and one on the third. Okay, and for two intersecting lines, that's clear. In fact, we have this situation in our discussion, two intersecting lines. Okay, I'll tell you what that situation is. Okay, first, plane containing a point and perpendicular to a vector. Okay, plane containing a point A and perpendicular to a vector. So here we have got A known point on the plane. Okay, here we have got A as known point on the plane, and n bar is perpendicular to plane. Now n bar is a free vector, let me tell you. Okay, n bar is a free vector. Okay. Now suppose P is any point on the plane. Suppose I join AP bar. Okay, suppose I join AP bar. What will be the angle between AP bar and n bar? This being a free vector, I can place it here, right? What will be the angle between the two? 90 degrees. So AP bar is normal to n bar. AP bar dot n bar equal to 0. And if we want the Cartesian form, let us assume that A, B, C are components of n bar, and A has coordinates x1, y1, z1. So we will get x minus x1 upon into A plus y minus y1 into B plus z minus z1 into C equal to 0, or ax plus by plus cz, let us write d there, is equal to 0. Now this is the linear equation in three unknowns, and that represents a plane. This is also called general form of equation of plane. Okay, if C is equal to 0, okay, if A, B and D are 0, then we get and C is equal to 1, then we get xy plane whose equation is z equal to 0. Okay, so this is general equation. And there is one interesting point which you may be already knowing. In the general form, coefficients of A, B, x, y, z always tell us the vector normal to the plane. Okay, ai cap plus bj cap plus ck cap, they always tell us the direction ratios of the normal to the vector. Is this part here?
Yes, sir.
Okay. Now, plane through a point and parallel to two vectors. Okay, plane through a point and parallel to two vectors. Let me first write down its vector form, and then I will return to the situations that we discussed earlier. Okay, look, B bar and C bar are free vectors. Parallel to plane. Point A is any, okay, known point. Okay, it's a known point. It is a known point on the plane. Now, can I say that AP bar is perpendicular to B bar cross C bar? Yes, because if B bar and C bar are coplanar or parallel to the plane, then the perpendicular vector to them will be B bar cross C bar. So R bar minus A bar dot B bar cross C bar is equal to 0 because scalar triple product of three coplanar vectors is 0. That's one thing. Or as AP bar is perpendicular to B bar across C bar, AP bar has to be, well, when we take its dot product with B bar cross C bar, we should get 0. Have you got this?
Yes, sir.
Now this also covers two intersecting lines case. If we consider two intersecting lines as R bar equal to A bar plus lambda B bar and R bar equal to excuse me, A bar plus mu C bar, okay, A bar plus mu C bar, then those lines will pass through A and then we can just follow this. Okay, other things can also be covered in similar lines. Okay, let's say a line and a point not on the line. So here we can consider a line as R bar equal to A bar plus lambda B bar and a point on R bar equal to A bar plus mu C bar, or we can also reverse the roles of these lines. Okay, fine. And for parallel lines, how does that situation work? Okay, we will discuss it later. But you got the point, right? Once you got this point and line, you can do it anything. Okay, let's do it here. Okay, you can say two parallel lines. Okay, so what I'll do is I will take 2 points on R bar equal to A bar plus lambda B bar. Okay, now I need a third point. Okay, see, if I have two parallel lines, then I should know the second line's equation. Okay, let us say some A1 bar plus UB, and then I can find the equation of the plane. You got the idea, right? Or should I explain it again?
Got it, sir.
Take it. Yeah, plane through three non-collinear points. Yeah, actually this comes under three non-collinear points. Let me shift it there. Yeah, okay. Suppose we have three non-collinear points given. ABC known non-collinear points on the plane. Okay, fine. And P is a variable point. Now because these 4 points are coplanar, I can say that AP bar dot AB bar cross AC bar is equal to 0. And that gives us everything. Okay, now how can we consider parallel lines? Let's say we have 2 points on R bar equal to A bar plus lambda B bar minus A bar. And suppose I consider this one more line which passes through C bar or point C and which has the same direction as that of AB. Okay, so basically I'm talking about these two lines. One that passes through A and the one that passes through C. Okay, and then the distance between them. But not the distance, we can pick a point C here, AB here, and any other point, we can apply the same logic here. Is that clear?
Yes, sir.
Right? Okay, fine. No, if you find it difficult, please interrupt me, okay? Otherwise you will keep on saying yes to everything I say, and then while solving the problems you may not understand the problems completely. I hope that's not the situation. Okay? Okay, now let us come to the normal form. So in normal form, what is given is there is a plane and we drop a perpendicular from the origin to that plane. Okay, what we do is we drop a perpendicular from origin to that plane and length of OM is given. Okay, and direction cosines of OM bar are also given. Then the equation is Lx plus My plus Nz equal to P. This is similar to formal form of line, okay? In two dimensions where we say x cos alpha plus y sin alpha equal to P. Now why do we write sin alpha here? Because here it's actually cos of pi by 2 minus alpha. Okay, so for two dimensions theta x and theta y are always complementary. Theta x plus theta y is always 90 degrees, right? So that works. Okay, you can derive it, but let's just skip the derivation. Normal form Lx plus My plus Nz equal to P. Now suppose I have an equation like this: 2x plus 3y plus 6z equal to 9, or let's say 7. How can I reduce it to normal form? See, to reduce it to normal form, make sure that these coefficients form a unit vector. Okay, currently I only have 2y plus 3j plus 6k. So for n cap, I have to divide them by 7, right? 7 is the magnitude of that vector. So if I divide this by 7, I'll automatically get what I want, or what I call the normal form. Okay, so it's x by 7 plus y by, sorry, sorry, not x by 7, 2 by 7, sorry, my mistake, 2 by 7x plus 3 by 7y plus 6 by 7z is equal to 1. Correct? So P is equal to 1 here, because it's this is the normal form and this is the general form. Clear? It's not too heavy, right? Only theory, theory, theory.
It's fine, sir.
Okay. Now let us discuss the family of planes. Okay. Now, if we take any two intersecting planes, okay, when any two planes intersect, their intersection is always a line. Okay. So consider red plane P1 and blue plane P2. Okay, their point of intersection is a line, and the equation of any plane through this line of intersection is of the form P1 plus lambda P2 equal to 0. Okay, let's say P1 is equal to 0 and P2 is equal to 0. Okay, so what is P1? P1x plus B1y plus C1z plus D1, and P2 is A2x plus P2y plus C2z plus D2, and when you equate it to 0, you get the plane. Okay, now this is analogous to family of lines. Okay, this is analogous to family of lines. Okay, you remember there we take u plus lambda v equal to 0. Here we do the same thing. Okay, as we vary the value of lambda, we get all the planes which share the same line of intersection with the other two planes. Clear? Okay, fine. Now let us discuss the intercept form. similar to or analogous to double intercept of line. So there we have x upon a plus y upon b equal to 1. So here we have a plane passing through the points a0, 0, 0, b0 and 0, 0, c. We can find this intercept form using the equation of plane passing through three non-collinear points, but when simplified it becomes this. Okay, next topic is length of perpendicular from a point on a plane and bisector planes. Now this situation is also very similar to a pair of straight lines and length of perpendicular from a line from a point on a line. Okay, now look, suppose we have a point P and suppose this is the plane. Okay, suppose this is the plane and suppose we want to know what is the distance between the point P and the plane. Okay, the formula is, suppose the equation of the plane is Ax Py plus Cz plus D equal to 0. So Pm is equal to mod of Ax1 plus By1 plus Cz1 plus D divided by under root A squared plus B squared plus C. Okay, that is actually the, see, if you remove, if you make C 0, that will reduce to the equation, the formula for length of perpendicular from a point on a line. Okay, now let us go to bisector planes. Same logic. If I drop a perpendicular from any point on the bisector to both the lines, it should be same in length, same thing. Okay, now let us suppose that the blue plane suppose that the blue plane bisects this angle. Okay, so this is theta and this is theta, and there will also of course be another plane which will be the obtuse angle bisector. So equation of that blue plane and the other plane, how will we find that equation? Okay, suppose the equation of the green plane is this time θ equal to 0, then we will get a1x plus p1y plus c1z plus d upon root of a1 squared plus b1 squared plus c1 squared equal to plus or minus a2x plus b2y plus c2z plus d2 upon root of a2 squared plus b2 squared plus c2 squared. Okay, so those are the two bisector planes. We can also determine which one of them is the obtuse angle bisector and which one of them is the acute angle bisector. If you want, you can figure it out. It's basically, we have discussed that in pair of straight lines, if you remember. Okay? Yeah, okay. Similar to line and point in 2D. Similar to angle bisector of lines. Okay? Fine. Next part. Fine. Angle between two planes. Now this is something which we have already seen. Now the fact that I am going to use, I have already told you this when we were discussing equilibrium problems in physics. okay, or motion of the block sliding. There I made a statement that angle between any two lines, so I modify it and say angle between any two planes is angle between their normals. Okay. So suppose n1 bar is perpendicular to P1, plane P1, and n2 bar is perpendicular to plane P2, then the angle between the planes P1 and P2, that is theta, will be the angle between the two vectors n1 bar and n2 bar. Okay, so how will we determine the angle? Cos theta is equal to n1 bar dot n2 bar upon mod of n1 bar into mod of n2. Okay, and if you want it to be acute, then take mod. Okay, if you want the angle to be acute, then take the mod. Got it? Simple, angle between two planes. Now how can we determine angle between a line and a plane? Now see, here we have to use the same formula, but we have to make sure that we take the sine of the angle. So why sine of the angle? Look, we find the angle between normal to the plane and the line M. Okay, so that angle is cos given by cos alpha equal to n bar dot b bar is a vector along the line, upon mod of n bar into mod of b bar. But alpha is not the angle that we want theta. Okay, but what is cos of alpha? That is nothing but sine of theta, as alpha plus theta is equal to pi by 2. And there you get the answer. Is it clear? Well, you better take the mod. Fine, so you take sine theta there, everything else remains the same. Is it clear, or should I explain it again? Okay. Yeah, now I just wanted to discuss these things. If we take sphere in 3 dimensions, let us say the center is HKL and radius is A. Then the sphere will have equation x minus h squared plus y minus k squared plus z minus l squared equal to a squared. That is the center radius form of sphere. Okay, center radius form of sphere. So then you may ask, what is this equation? What does this equation represent in 2 dimensions and 3 dimensions? This is a circle in 2D, but it is actually a right circular cylinder of infinite length in 3D. Whose axis is parallel to z-axis. I will show it to you and then I will stop. So let's take a point. And let's draw a sphere whose center is A and whose radius is 4. X minus 1 square plus y minus 2 square plus z minus 3 square is equal to 4 square. That's the sphere. Okay, that's the sphere, and as you can see, its intersection with the xy plane is a circle. Okay, now if I just say x minus 1 squared plus y minus 2 squared equal to 16, I'm actually going to get a cylinder which will pass through the same circle of intersection between the sphere and the xy plane. Okay, oh sorry, not that, it will, oh sorry, I made a mistake. It should be such that its radius is equal to that of the sphere. Okay, So this is the cylinder, and if I take its projection on the xy plane, I'm going to get a circle whose equation is x minus 1 square plus y minus 1 square equal to 16. Okay, that is a cylinder, contains origin, radius is 4. Okay, and similarly you can get curves like paraboloid, surfaces. Okay, should not be called paraboloid as a curve. Okay, that is a paraboloid. Now why is it a paraboloid? Because if you take its intersection with the let's say yz plane where x coordinate is 0, then you'll get a parabola. Okay, then you'll get a parabola like this. Okay, so it's and if you decide to rotate it about its vertex, you'll get a paraboloid. Okay, it's called paraboloid. Okay, fine. So I'll stop here for today.